Okay, then the second method that is called sacrificial template method. It's also, let's say, quite easy. We have our ceramic powder or a slurry or a ceramic precursor, but it's important to keep in mind that it will be in solid, like only a dry powder, or in a liquid form, like a slurry. We will add different phases that at the end will be your porous structure, and it's called sacrificial material because before the sintering we will eliminate this material, okay, and then we will do the sintering, and of course at the end that we will have is the porous structure, okay, with the shape of this sacrificial template. Again, a lot of possibilities to do it, and also using different sacrificial templates, organics, resins, liquids, salts. The combination is quite large, and it's possible. Typically, and this is quite easy to do, is just two steps. You mixture your components. For example, if it's in dry, that is the easy one. You have your ceramic powder, you have your other particles, maybe polymer particles, okay? We mixer and press it, and then we have our pellet, and well, we will remove it. The advantage, for example, is that we can do different suspension of slurry that are really homogeneous between our powder, and then we can do different processing steps, like we explained in the first day, and then we can process different shapes or complex shapes, okay? Well, again, like in the first method, we need to extract or to remove these templates that we have incorporated these particles, okay, and then the typical is to eliminate them by firing, okay, normally at this temperature, because obviously the components that we want to add has a low melting point, okay. But again, and this is important, it's like in the other one, like we are removing material, it should be low heating rates, okay, because if not, our material will be cracked, and for that reason, it's always taking long periods to do it, and is one of the main disadvantages. But here is one solution, yeah, exactly here. Well, this problem can be solved or overcome using other strategy, that is through the extraction. Here, these particles, as until now we have talked that you can burn out, okay? But for example, imagine that you add here sodium chloride, okay? And then you introduce in water, and then this sacrificial template obviously will be just dissolved, okay? And this is the example of that one. Use, for example, a salt or a ceramic that by water immersion, for example, this salt is eliminated. Then first you save one step, well, you change for other, but save one step that consumes a lot of energy. This is then quite important for companies or other methods. The only problem is if you add as template ceramics or metal, then requires, let's say, really aggressive method media like acids or basics that attack your material. But if you use, for example, salt, that is the most common material in that case, it's just quite easy. Do it by water immersion, okay? It's quite flexible and quite easy. And well, just to keep in mind, I think so there are different things, but it's important that you keep in mind that the porosity in that one is only let's say until 90%, but it's also going from really low values, and that one, this is quite important, because the other has a really large porosity, and this one we are more flexible in that between 20 and 90%, and also between the pore size. Here is between 1 and 700 microns, okay, that is quite broad. And well, here there are a few examples of different microstructures using titania or, well, oxide titanium, and different structure how they looks like, okay, just to have in mind for you. And here again, well, it's not that work, but it's one work that we did in Fortune Century Julie using this max phase that yesterday we comment, because the idea of that one is use a really high porous structure to be on a really high temperature and use at heat exchangers, and then we do that. We mix our powder, okay, with this space holder that in that case was this organic compound that has a low point to evaporate them. Then we mixture, we press, we heat it up, step by step. We mixture in a combination of 30, 50, and 70 volume percent of this temporary space holder using different sizes, okay? Between 90 and 180, 180, 250 microns, and 250, 400 microns of this porosity, okay? Then we heat until 80 degrees to decompose this material and then generate the gas, and it's removed for 10 hours, okay? And then do the pressureless sintering or our material to obtain the final compound, okay? And well, here is a graph that you have an idea, okay? This is the space holder amount or content that we add, okay? This 30, 50, and 70%, okay? This 30, 50, and 70%. And this one is the porosity in the final material, okay? Measured. And as you see, well, first mention that if you sinter this material without any space holder, it's already porous. You never achieve the full densification, but for the material that we are talking, it's exactly here. This is the theoretical 30 with 30, and as you see, it's really close. I mean, the volume that you add at the beginning that you add at the end. Even here is totally close. It's always less than 5%. Then even once that you have your graph, if you need, I don't know, 50%, you just need to calculate what is the amount of pores of this temporary space holder that you need to add. But this is quite good. Another thing that is important of this method, even adding different particle size, always the occurrence is the same. I mean, and it's quite hard. For that, this method is also quite flexible. And here a couple of microstructure about this material. One case for 30%, another for 50%, and one for 70%, and with a different particle size, okay? With the smaller, with the medium, and with the large one. And this is after the sintering, to have your idea. A few things that should be highlighted is that there are homogeneous dispersion of this material, and just was mixing by hand this space holder with the powder. And important, and I think is, well, maybe it's even better there, but the porosity of our material, as you see, is that one, of course, by those space holder, but also this micro porosity that is caused because the matrix is not full densified, okay? Then this micro porosity connect also the pores. And well, just to keep in mind also, I mean, it's really wide, this material, even for 30 to 70%, and the homogeneity and everything is quite good. Then it's a really high reliable method to do this, from low to intermediate to really high porosity material. And well, here just another example in more detail, the fracture surfaces. Well, as you see the microstructure, and here just to mention the walls between two pores, one pore and here other pore, the wall are really thin, is less than 20 microns, and the mechanical stability is quite good. And between these two pores, obviously also are connected by this microporosity. And well, here just one example of the MAC phases that we talked yesterday about these really great mechanical properties for this layer structure of these ceramics. And well, going in that direction with that idea, the idea was to perform a heat exchanger, and then just in dry, advantage of these MAC phases, we press pellet of our material. We did a hole with a machine, I mean, in the green state, and it survived. We introduced a commercial tube, and we sintering or porous structure, okay? And at the end there is a really good attachment, and this part is a porous structure like that one, okay? It's a 70% even. And well, after that, well, we analyze the interface between our tube that is here and our MAC phases that is there, And well, some of the titanium, of course, diffuse to our material, but this is not a big problem because as we analyze by TDS, this titanium tube, all the titanium tubes are always present with the aluminum, and our material present titanium, aluminum, and carbide. Then the compatibility is quite good, and the adhesion for that reason is excellent. Okay, just that one was to show you an example in a lab scale. And well, the last method, that is direct foaming method. This one is a little bit more complex and depends in a lot of things, but at least just to show you that we have is our suspension from the ceramic. Again, as always, a precursor of the ceramic, but have idea your suspension with low viscosity, a liquid, and then we introduce a gas, like like Coca-Cola or wherever. You introduce a lot of gas, then the gas is introduced in your material, you incorporate it, but this gas cannot be released because the viscosity of your material is high enough. Then you dry it and sinter your material, and obviously at the end that you have is the shape of these foams. Okay. However, it depends of a lot of things. Okay, because well, obviously it depends on the amount of gas that you incorporate, or at least that you can keep in your liquid, and the pore size is more complex because it's determined by the stability or the interaction between your gas and your material. Okay, and then well, it's a little bit difficult because depends of several things, how these foams are stable thermodynamically with the time in your system, because well, there are different methods or processes that reduce your porosity, and well, it's so critical how to stabilize your suspension. But mainly, well, there are two kinds of methods to do it: is using a surfactant or adding with the particles. Okay, and here is just one example to have ideas your foam stability. One of the problems is that normally the gas it's accumulate always on the surface. I mean, like example like the beer, for example, is something like that. The stability at the end of the foam and drain and go up. That is this Oswald ripening is not homogeneously distributed at the end, and here the porosity will have different properties. Okay, and also well, this coalescent method that plays against us, it's about how the stability of two bubbles in contact with a wall, but well, depend of the distance and the Van der Waals force, and that we can play with that. This is the idea, at least, that you have in mind, because well, add different effects like the Van der Waals attraction between bubbles, but also the electrostatic repulsion between them. Then you should play with that and add in different organic components. Okay, and well, just here different examples. This Oswald ripening, we have our homogeneous suspension, but after 4 hours, by this process that we talked, the pores start to grow and grow. But if you add some gas molecules, you can keep stable your suspension. Okay, then this process is more difficult. Here some molecules that you can add, commercial one and from different companies, big companies, but at least that you have in mind. I mean, it's possible to process several materials, but in that case is more complex. Okay, and well, the advantage of that one is that you can achieve a really large porosity or the pore size, and also the porosity that range between 40 and 90%. But also the good part is if you really can control your bubbles, you can go until really high value. And well, one of the advantage is that all your pores will be spherical, because obviously the gas inside the liquid has this spherical shape by the energy, they minimize the surface energy. Okay, and well, here is just for the finishing one application of this porous structure that maybe is interesting for some of you. If you want to combine well, I don't know, for example, different things at high temperature or different thermal protection, but also with a porous structure and so on. Okay, because for example, we talk all the time in aerospace, if you want to save energy, lightweight structures, Then you need different things like low density, high strength, that also is a really excellent insulator. Then we should combine things, okay? And we talked during these days about the fibers, okay? And this idea is copy the nature, I mean, directly, okay? It's like the bird's nest that you have your fibers, okay? Made by different goods that they find in the nature, but they use wood from different animals in order to do the insulation, okay? The network is to have enough mechanical stability, but to keep warm the animals, they use this wood as a thermal insulator. And then that was the idea, to use fibers to have the mechanical stability and a really lightweight structure, because they can be porous, and fill it with this zirconian silica aerogel who has low thermal conductivity, okay? Just to mention, they use mullite fibers with this diameter and length, and this aerogel for the thermal insulation with a really high surface area, okay? In just 1 grain is 82 square meters, okay? That is quite hard. And what they do is like this method. They produce is mullite fibers are totally like connecting between each other. They introduce in this organic bonder, then they have the green, they sintering, and at the end they do the impregnation, and at the end they have the composite material, okay? But here, to have you an idea, this is the really, it's like a phone, but everything is done by the fibers. And now, to insulate the material that they add is this aerogel based on zirconia and silica. At the end, looks like that. The increase in volume is, as you see, is 0. I mean, they don't increase, they just coated this some of this small gap. And at the end that they have is a really high porous material. 90% of this material is porosity, is air, is nothing, let's say, with a really low density. This density is quite low of this material, okay? And that's the idea. They have enough mechanical stability that these fibers, but they protect with this aerogel. And well, here more pictures about this idea. Is really highly porous and well coated by these nanoparticles. And probably is here the also the mechanical stress, how it failed, and hopefully is the thermal conductivity here, okay? Obviously the thermal conductivity increase at high temperature, but as you see it's really low, the thermal conductivity, even at high temperature. And this one is because they have this really high porosity and porous material. And just to mention, the compressive strength for a material with a porosity close to 90% is quite good, okay? And yeah, that's all. If you have questions, that's the moment, or now in the pause. Yeah. Question? No? Okay, then. Sure. Sorry.
Hi, my question was about some materials that appeared, I think, like half a year ago, that are called metallic microlithises, I think. That is like 99.99% air, and it's an structure of a metal that is surrounded by air. I don't know if is there any investigation that you know about that, because it looks really interesting.
I know when I was preparing that one, exactly about one metal that even is lighter, let's say, in the air, that if you have it, it flows because the density is quite low, and they want to use it as a TPS, like a thermal protection system also, because of course if you have practically no material and it's porous, your thermal conductivity is quite low. But it's everything that I know. I mean, I heard about that, and I see that was about metallic foams, but I don't know more about the properties. But I know that are really lightweight structures, but are metals. And then what the idea here is to show how is the state of the art, but in ceramics material. But of course, it's going in that direction that in some way, it's totally different, but I mean, the idea is to do something like that, a really highly porous structures that in some way are reinforced to keep it, because obviously you have 90 or 95 or 98, I mean, really high porosities is quite hard to keep the mechanical strength.
And in this case, is there any possibility to change the orientation of the mullite fibers to make it anisotrope?
Sure. I mean, if the only problem with that is that probably like you will require maybe some pressing or some processes. Probably you will decrease. Probably I don't know. I don't do it, but your final porosity. But of course you can orientate this fiber. But the idea, and as I told you here, my idea is to show you how we also copy the nature. Okay, this is like the burst. Okay. You can orientate, but if you want to keep the mechanical stability, the good part is that all the fibers are totally surrounded, protecting your material. Okay, but of course you can orientate by different methods and do it. But here I think the idea is that it's like a mesh, and then it keep it. Okay, but of course you again like your imagination can do. If you think that for some application require the orientation or something like that, then of course you can do it. No doubt.
Okay, thank you.
Yeah, welcome. More questions or comments? No? Okay, then see you in 15 minutes at around 11 o'clock, okay?